All right, good morning, everyone. So last time we were talking about a way of doing feature selection, which is determining which subset of features we want to use in our model. We have a way of doing that using what we call regularization, which is where we take the loss we're usually interested in minimizing, and then we add a penalty term or regularization term. Here's a couple of varieties that penalizes our use of beta, encouraging us to use either, in this case, we saw this encourages us to use smaller value betas, and then this one encourages us to use more zero value betas or fewer betas, and therefore it does feature selection. So these are the two we've talked about. Ridge regression is where you have RSS plus the Euclidean, squared Euclidean norm. And then Lasso is where you have RSS plus the one norm. And so both of these norms are ways of measuring the length of that vector beta. The Euclidean norm is the one we're more used to using. It's just the straight line between 2 points, whereas the L1 norm measures distance by the sum of the absolute values of the distance of each coordinate. And we saw that, so when we use ridge regression and we increase alpha, we notice that the coefficient values, they shrink to zero. Asymptotically, they become zero, but you don't get any exactly zero valued coefficients until you push alpha to infinity. So it's not actually doing feature selection, but when we looked at Lasso and we looked at its coefficient path, we noticed that as you increase alpha to some finite value, the coefficients start turning off one after another, and eventually they're all exactly zero, but the interesting part is when some subset of them are zero and then the others are non-zero. So Lasso is going to be useful for feature selection, but there is kind of a downside to Lasso, is that even when you have found, in this case, a subset of 3 features that you want to use, the coefficient values that Lasso selects for those features is itself biased towards zero because of this regularization. And those coefficient values are no longer going to be optimal. And so instead of using them, we suggest to determine which coefficient indices we want to use, which features we want to use, and then just do a least squares fit to those features alone. And then that will get rid of the bias. So that's what we talked about last time. And here we'll just go a little bit more into some of these details with the implementation in sklearn. So one of the main thing to talk about with Lasso is how do you select this parameter alpha. So we would like to use some cross-validation method. And I'm going to first present one method, and it's actually not going to be the right way of doing it, and then I'm going to show you the right way of doing it later. So this is sort of maybe the way you'd think about doing it, but in the end, it's not quite right. So imagine that we first create this k-fold object. This is with the k-fold method in scikit-learn. And if you remember, what this does is it sets us up to do k-fold cross-validation. And once we have this method, we can have 2 nested for loops, where in the outer for loop, we keep calling this k-fold object. And what it does is it gives us some index sets. And the index sets show us which indices we can use for training and which for testing for that iteration of k-fold optimization or k-fold cross-validation. So that's why we create this k-fold object. And the other thing we're creating here is this is our Lasso object. So we're setting this up in exactly the same way that we have previously set up our linear model. And we use it in exactly the same way. So once that's set up, here's our inner loop. Our inner loop So our outer loop is over the folds in k-fold, and then our inner loop is going to be, we're going to make a grid of different alpha values, and we're going to test each alpha on the grid. So this is very similar to what we did for model selection in the last unit, where we tested different model orders. Now we're testing different alpha hypotheses. So our alpha grid, we made it over here. So this is just a log-spaced grid from 10 to the minus 3 to 10 to the power 1. And so here when we look at our inner loop, we have, first what we do is we set the value of alpha in our Lasso model. So let's go back and remind ourselves what that is. So in Lasso, we have to select the strength of the regularization alpha. So that's what we're going to select in this line. We're going to tell k-fold, or sorry, we're going to tell our Lasso object we want to use the alpha that is the particular one in this vector. And then we fit the Lasso model on the training data. So internally, it runs a convex optimization algorithm. It determines what those beta coefficients are, stores them. Then we use those beta coefficients to predict the test labels from the test features. And finally, we evaluate the mean squared error by looking at the difference between the true test labels and the predicted test labels. And so we go through this for loop, and in doing so, we create a matrix of mean squared error values. Along one dimension, you have all the different alphas that you've tested, and along the other dimension, you have all the different folds. And then we can average them across the folds to get, let's see, there's probably a picture coming up. Well, I don't have a picture of exactly this, but you can now have a mean squared error versus alpha. You can also look at the standard deviation, not just the mean, and this will give you, here what we're doing is we're actually computing standard deviation divided by the square root number of folds, which, as you know, this is the standard error. Okay, so if you wanted to do one standard error rule, you would need to compute this standard error here. And then this is our MSE versus K, where K is the fold. Actually, sorry, we've actually averaged this. So this is MSE as a function of alpha. We've averaged across the folds here. So one thing you could do then is you could say, okay, I've tested all these alphas. I can now find the alpha which gives me the lowest MSE on my test samples. So this is one option. Just a quick comment that there's a shortcut. The shortcut is to use a different command, grid search CV. And this grid search CV is a way of having scikit-learn automate all this double loop process. We'll see some examples of grid search CV coming up, but all you have to give grid search CV is your k-fold object, you give it your estimator lasso, and you give it your vector of alphas, and then it does all this stuff for you, and it basically gives you this matrix back. Okay, but this one is a little bit clearer to see it the first time, so you see exactly what we're doing. All right. So on the previous page, we have found the alpha that minimizes MSE on the test fold. So we don't want to use the Lasso coefficients directly because we know that the coefficient values are biased towards the origin. So they're smaller in magnitude than we would like. So instead, we want to look at just which of the coefficients are non-zero. And I recently made some modifications to the demo, and I noticed that there's an error with this. Somehow, I have to see what the problem is, but there's a discrepancy here in the. I'm saying that Lasso selects only 3 features, but there's not 3 features here. As you can see, there's actually like 1, 2, 3, 4, 5, 6, 7 features that are non-zero, and only 1 feature that's 0. So I'm going to need to figure out what the bug is, and I'll fix this problem. But the point is that Lasso has, at this point, selected some subset of features for us. And let's just assume there was 3 of them instead of 7. So then what you do is you say, okay, I know which features I want to use in my model. Now I'm just going to go back to least squares, and I'm going to fit my least squares coefficients on those features. And least squares is unbiased, so it gets around that bias problem. So that's the key point here. So you isolate those features and use them for least squares-based linear regression. Why? Because the non-zero coefficients in the beta lasso vector are biased. So we would like to avoid them. Okay, so in terms of the code here, you can see that once we find alpha min, the optimal alpha from the previous page, we tell the Lasso object to use that alpha, and then we can fit Lasso on the entire training data, rather than, because in k-fold optimization, we were only using portions of the training data. Now that we've decided alpha, we can use the entire training data. And we can print out things like the coefficients, the cross-validation, mean squared error, and so on. And so one comment is that when you actually look at the value of the cross-validation mean squared error, it's not very good. Even though Lasso has decided not to use some features, because its coefficients are biased, the features that the coefficients that it has decided to use actually result in a relatively poor cross-validation MSE. So we just want to use Lasso to tell us which features to use. We want to use it for feature selection alone, not for the coefficients themselves. So this code below is what shows how we can isolate those features. So here's the Lasso coefficients. So you can extract the coefficients from that Lasso object by doing .coef. So this will give you the vector of coefficients. And then you look at the absolute values of those, and then you ask, where are those absolute values greater than 0? And this will return for you a list of indices, and we store those in this subset vector. And then here you can see this is the X training matrix. So when we go down the rows, we have all our examples. When we go across the columns, we have our different features. And by putting in this subset, I'm only going to index the features that I want to use. And I'm going to leave all the other ones out. So this is how we're doing, this is how we're extracting them. And then notice that I'm using here the linear linreg. That's just the least squares model. That's linreg. So isolating the features here. I guess I'll erase this arrow. And then what we're trying to do finally here is understand how well this procedure works. So that's why we're using cross-validation score. So this is going to take this model on those features, and I'm going to give it this repeated k-fold object. I'm telling it, do cross-validation that way, look at the negative mean squared error. and it's going to evaluate using k-fold cross-validation what the mean squared error is. And then we can look at it and we can notice that this has improved relative to here because we're using the same features, but we are recomputing the coefficients in an unbiased way. And so that's why we get the improvement. Okay, so covered a bunch of stuff. Are there any questions about Lasso? Yeah.
Are we still going to standardize the target and features when we use the least square again?
Yeah, so the question is whether you need to standardize the data when you use least squares. It turns out it doesn't matter. Least squares gives you the same, it gives you the same predictions in the end, whether you standardize the data or not. But it's just, since we've already standardized our data at the beginning, it's just simpler to use the standardized data for least squares also, rather than go back and use a different data set. So in the demo, we just use the same standardized data for everything. And I would say that's what's common, is you just standardize your data at the very beginning, and then after that, you just use that standardized data for everything. Okay. Yeah, go ahead.
So why isn't Lasso and Ridge Regression called that name?
Well, why do they have those names?
Yeah.
That's a great question. I don't know. So the inventor of Lasso is one of the authors of the Elements of Statistical Learning textbook, which is one of the famous textbooks, and it's one that I think I have it on the optional textbook list. That book might explain it. I don't know. But it was these statisticians at Stanford that came up with this stuff. So there's probably somewhere you can read the history, but I'm not sure exactly where the names came from.
Apparently Lasso is least absolute shrinkage and selection operator.
Yeah, that sounds right. Ridge, I don't know where Ridge came from exactly. The funny thing about Lasso, though, is in a lot of papers, people just write it without the capitalizations, like they don't even think of it as an acronym. They just write it with all lowercase or with a capital L, and then so even that acronym somehow has been lost because it's so commonly used. But all right. So any other questions on what we've done so far? So there is a problem with what we've done so far. I don't know if anyone's noticed it. The problem is that we selected alpha. Let's go back to how we selected it. We selected alpha based on how well the Lasso coefficients performed in terms of mean squared error. And then we threw away those Lasso coefficients and replaced them with least squares coefficients. So the problem is that our alpha was selected based on how the Lasso coefficients work, and we don't care about those Lasso coefficients. Really, we should be selecting alpha based on how well the least squares coefficients work after feature selection. So that is the proper way to do it. So that's what we're doing over here. And I'm calling this overall approach where you first use Lasso, determine which coefficients you're going to use, and then you use least squares to determine what the coefficient values are. I'm calling that Lasso plus least squares. And that's what we want to tune, is we want to tune that overall combination of techniques. So again, in words, the alpha on the previous page was selected to minimize the RSS of the Lasso coefficients, but those coefficients are biased, and we actually threw them out. We should instead tune alpha to minimize the RSS of the Lasso selected least squares coefficients. So it's not too different to program this. The result is shown over here. So what we do is we make a grid of many different alpha values, and we test each of them on the grid using k-fold cross-validation. But what we're testing is, so first we design Lasso, then we look at the non-zeros, then we design least squares, and then we measure the performance of the least squares estimator just as we've done here. So these scores, those ones are what's plotted here. So this one, yeah, this is the mean. This is like, you could say, this is the mean squared error as a function of alpha. And as you can see, you have a sequence of flat lines. So why is that? Does anybody have a guess of why we have like a flat line and then a flat line?
No other coefficients went to 0?
Exactly. So what we did over here, we gradually increased alpha, but the set of non-zero coefficients was the same, and so the least squares estimator was the same, and then all of a sudden right at here, we turned a coefficient off. So now we have fewer coefficients, and then as we increase alpha, the same number of coefficients are there, the least squares error is the same, and then here another coefficient got turned off, and so on and so on. And so, so finally you get the sequence of flat curves, and you can see that all these alphas here resulted in the same least square, the same coefficient subset that we use for least squares. So all of these alphas are equally good. We'll just choose the first one there, and that's the alpha that finally gives us the best mean squared error for the final least squares estimator. We can also visualize things in this printout here. So when we were down, okay, actually, this is when we have a single feature selected, and in fact, that is where we were up, I guess up here somewhere. So if we start with a high alpha, here we have a single feature, then all of a sudden here we have 2 features, then we have 3 features, and here I'm printing out which those features are. First we had feature 0, then we added feature 4, then we added feature 1, then we added feature 7, and you can see the mean squared error goes down, and this is the best 0.386, which is when we had 3 features. That's this level of mean squared error. So, so this is how we really want to do feature selection with Lasso and tuning it. Okay, is it making sense? Yeah.
And at the beginning of this, you showed that we could test every single possible combination of the betas.
That's a possible, yeah, we can test every combination of the betas if the number of betas is small, if the number of coefficients is small.
Is this Lasso plus least squares going to give the same performance?
It's a great question. Let's see. So the demo tests a whole bunch of these methods on the same problem. And then here, it's printing out the performance of all the methods. So this exhaustive search plus least squares is giving 0.386. That's the best. We expect it to be the best. What about Lasso plus least squares? Lasso plus least squares, same exact value. That's because Lasso plus least squares selected exactly the same subset of 3 features that exhaustive search selected. So they both narrowed down those features, they both use least squares to fit them. So that's why they have exactly the same performance.
Will it always be that case?
We'll not always see this. This is just what happened in this demo. Lasso is not guaranteed to be optimal, but it often works pretty well if you implement it correctly. So yeah, this is just one demo. Lasso is definitely not optimal. There are some theoretical results that actually show that in certain cases, Lasso is optimal. If the feature matrix is sufficiently random, like if this is just a kind of a theoretical thing, but if the feature matrix has random, independently identical like Gaussian elements, and you have enough measurements, then you can prove that Lasso is going to give you the same results as the exhaustive search. But that's just kind of a special case, and it doesn't necessarily translate to real data when you don't have random features. These are actually measured features from some experiments and so on. But it gives you some intuition that at least sometimes it works optimally. Okay, so what about the other extreme? The very first thing we tried was plain least squares. That's no feature selection at all. And that's the first one. You can see it's a bit worse, 0.404. None of these techniques are, they're all within a relatively narrow range here, but that's among the worst. What about ridge? If we use ridge regression only, that was a little bit better than plain least squares, 0.398. What if we use lasso and we use the lasso coefficients themselves, which are biased? Actually, this is worse than least squares because of that bias. Another thing is, what if we do the one standard error rule on lasso plus least squares? It turns out that the one standard error rule, let's actually look at it. We can see it from here. So this is the mean squared error. And then the error bars, this is the top of the error bars. So imagine that wherever these are our error bars. So if I want to do the one standard error rule, what I would do is I would say, okay, this is my minimum MSE. This is my one standard error above. So I would say my target is this level. And now I'd say, what's the simplest model whose MSE is less than the target? And you can see that basically it's only these are less than the target. Once I go to a simpler model, which is over here, all of a sudden it's above the target. So it's not feasible. So the one standard error rule here says stay with your original MSE minimizing estimate. So that's why this has exactly the same performance. And then the last two things to talk about are, this is the recursive feature elimination, where you start with all your features, you take out one, you take out another, and so on. And then what that shows you is it shows you a sequence of different subsets, which then you can use cross-validation to figure out which of those subsets you want to use. You use least squares to fit the parameters. And in this experiment, this also found those same three features, and therefore, because we're using least squares, it gave us the same exact error. The very last one is, what if we use mutual information? So we rank the coefficients according to how much mutual information they and the target have. And once we have the coefficients ranked from highest to lowest, now we have a model order selection problem. We say, what if I use the most important? What if I use the two most important? And so on and so on. And this gave us performance that was no better than least squares. Essentially, somehow it told us that you should just use all the coefficients. You shouldn't do any feature selection. So this didn't work out too well in this particular demo. Yeah.
A question about ridge regression.
Sure.
Kind of why we do it. Wasn't the whole motivation behind these feature selections to reduce the amount of features we're actually using? Does that have to do with our variance?
Yes.
But if ridge regression doesn't actually set anything to zero, how exactly, I guess, does that impact our variance?
Yeah, that's a great question. So if we're interested in feature selection, why are we talking about ridge regression? Because it's not doing feature selection. So what it does for you is it helps with correlated features. We're talking about it in this unit just because it's really easy to talk about it, because it's so similar to L1, to Lasso. So it's a convenient time to talk about it, even though it's not actually doing feature selection. So maybe that's the answer. So this correlated features, sometimes actually you want to use both of these together, because you find that even if Lasso tells you to use a small subset of features, they might still be correlated even within that subset. And then by using ridge regression in addition, you actually can improve the estimation further. So, so that thing they call the elastic net. And again, I have no idea why it's called elastic net, but it's the sum of the L1 and L2 penalties. So it's just another one of the tools at our disposal. And I should say there's many, many other penalties besides L1 and L2 that people have proposed. They have advantages, they have disadvantages, but these are the ones that are most commonly used. So that's why we're talking about them. Okay, that's a good question. Any other questions about L1 or L2 or any of this regularization stuff? Okay, so our next subject is going to be to interpret all this stuff we learned from a probability perspective, and it's going to give us a new tool, or a couple new tools. One of them is maximum likelihood estimation, and it will turn out that maximum likelihood estimation is going to be kind of a theme that we're going to use for the remainder of the semester. So it's sort of an important thing that we're learning here. So we have to kind of step back and just think about things from a fundamental perspective, from a simple perspective, to explain the main ideas. So when we think about machine learning, as you learn more about it and as you look at what all the different problems and methods are, what it all has in common is you're estimating the statistical parameters in a probabilistic model of the data. So like when we first learned about linear estimation, we came up with this particular model that had these coefficients linearly multiplying our features. And then we said, let's estimate those coefficients from the data and so on. So you could see things already there, but as we'll see here, there's a bit more of a rigorous perspective we can take, which will tell us, for example, when linear estimation should succeed and when it should fail. And it helps to think about things a little bit more probabilistically. So we're going to talk about two approaches, maximum likelihood and MAP. And so let's just start at the beginning, just for some perspective. Imagine that I have a random variable, call it capital Y, that depends on some statistical parameters which we collect in a vector theta. So here's an example. Let's say that Y is Gaussian with mean mu, variance sigma squared. So I can stick those two parameters, mu and sigma squared, in a vector theta, and now I know that this probability, or this random variable, depends on these parameters theta. Okay? Now to visualize things, what we typically do is we plot the probability density function of Y. And when we plot it, we have to decide on some fixed values of those parameters. So here's an example of a plot for a particular mu and a particular sigma of this Gaussian. And you can recognize this is the standard bell curve. And as we know, mu tells us where the center of the bell curve is, and sigma tells us about the width of the bell curve, right? So in plotting this, what we've done, and this is very important, we plot this PDF versus Y for some hypothesized or fixed theta. So fixed theta, plot Y. That's what we tend to do when we think about random variables. Is everybody good so far? Okay, so in maximum likelihood estimation, what we're given a data set. And the data set are examples of that random variable Y. And our goal is to determine what theta is given those examples. So here's the framework that we use most commonly to do that. First of all, we assume that these samples are statistically independent of each other. So these guys are they all look like examples of Y, and they're all statistically decoupled. So as a result, what we can do is we can think of them all together, if we want, as individual random variables. They all have the same statistics, the same density, and they're independent. And so therefore we can write their joint probability, this is the probability jointly of all of them, equal to the product of their individual or marginal probabilities. Does that make sense? So like, if I just had two of them, probability y1 and y2 would be equal to probability y1, probability y2. That's what we're saying, except in this equation, we have n of them. N might be many of them. So we just have many things in the product. Okay, good so far? Okay, now here's the key point. We're going to use this to estimate theta for a fixed y, because our y's, we already collected that data. There's nothing variable about y. What's variable is theta, because we don't know theta. So we give this thing a very specific name. For this fixed set of y, the function py theta versus theta is the likelihood function. So fix y, vary theta. That's very different than on this page where we said fix theta, vary y. It's the same function, but what's key is what's variable and what's fixed. Okay, so now that we have this idea of likelihood, the way that we estimate theta is we just maximize the likelihood. So that goes like this. Find the theta that gives you the largest possible likelihood. It's like saying the data that I have, it's the theta that explains the data that I have observed. So that's the main idea. Is that making sense, or any questions about that? So this is the workhorse procedure of statistics and maximum machine learning. Okay, so we have this idea, but as you've probably seen from many different probability density functions you've seen over the years, they often have exponentials in them. And to make our lives easier, instead of maximizing the density directly, it's common to maximize the log of the density. And the reason why these problems are the same, so notice that this is an argmax. So we're saying that the maximizer of this is the same as the maximizer of this. So the actual value has changed because of the log, but where the peak is has not changed. And that's because the log function, the natural log, is a function that is monotonically increasing. So it preserves the order of all the samples that it sees. So the largest of these will still give you the largest of these, and that's why this will tell you the same theta that's the maximizer. Okay, so that's a very common thing, because this is going to be a lot easier to work with than the density alone. And then the last thing that's commonly done is in optimization, people often want to think about minimization problems rather than maximization problems. And so instead of maximizing the log, they will sometimes minimize the negative log. And now they can think about this as a cost, and they want to minimize that cost. So these are all the same. It's just that this is the one that you see most frequently because it's the most mathematically convenient. So that's the main idea. That is maximum likelihood estimation. So what we're going to do next is get some more intuition and start applying this to different problems. One kind of important thing to point out is that when you do this maximization procedure, you have put in no prior belief about theta. You simply are saying, for any possible theta, tell me the theta that maximizes this. You may happen to have an expert tell you that theta should be really close to 0, but here you're not using that information. That could be good or bad. It could be good because someone could say, well, you're not like influencing your results. You're not corrupting the data. But someone could say, no, it's bad because you're ignoring important information that you know. So whether you want to use this or not is just something you have to decide. We'll see another method, the math method later, is similar to this, but it actually does incorporate prior belief on theta, and that's what makes it different. Okay, so before we move on, any questions about maximum likelihood? All right, let's look at just a simple illustration that we can visualize. So here we have a model. Y is Gaussian with variance 1 and some unknown mean, theta. Okay, so we're just making it really simple. Our theta vector is just the mu, it's just this mu quantity. So for this, we know that the probability density function looks like this. So here's mu, we don't know that. Here's y, we do know that because we have observed some data. So let's keep things really simple. Let's assume that we collected exactly 2 samples, and they'll be called y1 and y2. And down here on the picture, I'm showing you exactly their values. So they are these 2 small positive numbers here, just for example. So what about the likelihood function? So we know that this is the kind of generating function of the random variable. So the likelihood function is probability of y1 and y2 for a hypothesized hypothesized mu. So the first step is always to assume that these guys are independent, identically distributed, and rewrite this as a product of the density of y evaluated at these 2 different samples, or in general, n samples. So this is the first, this is the first step, is to write this equal to this. The second step is to plug in the functional form of this density that you know. So when we plug that in, we get this. And now we have some sort of optimization problem. This is some quantity that we want to maximize as a function of mu. Mu is our free variable. How do we maximize it? So here I plotted below this guy here for 3 different hypothesized mu's. Let's say mu minus 1, mu 0.2, mu equals 1. And what I actually want to do is I want to look at the product of that at my 2 values of y that I observed. So in other words, if I'm hypothesizing mu is minus 1, these are the 2 numbers that I would multiply together to give me my likelihood. And now, as you can see, multiplying these 2 values is not very big. I can slide my bell curve over, and I can look at many other versions of hypotheses of mu. For example, here's another one, mu equals 1. It gives me the blue curve. These are the 2 values. I would multiply those together to get the likelihood. And it's not too hard to see. If you imagine sliding this bell curve everywhere, if I slide it right where the green curve is, then my 2 values here are very near the peak. I take the product of them, and I'm going to get a very high value. Do you think it's possible for me to move the bell curve over to the left or to the right to increase that value? What do you think? Again, we're looking at the product of the 2 heights of those dots. Can I move it and get a higher product? Probably not, right? So this particular mu in this example is going to be the maximum likelihood estimate of the unknown mu. This is our mu ml is 0.2. Right? So this is just kind of an illustration. You have to imagine for different hypotheses of the parameters, you end up changing the PDF, and you look for which of those many different PDFs gives you the best match to the data you collected. So that's just the steps illustrated. Right, is that maximum likelihood kind of making some sense? Okay, all right. So now what we can do is we can apply this to some problems that we've seen before, and we will see that we're able to recover things that we designed before without really thinking about them too carefully. So what about linear regression? So for linear regression, let's start with this model here. So this part is very familiar to us. Typically, we have in the past written things like y approximately equal to x beta. Now, notice that I'm using standardized data, and that's why I know that beta 0 equals 0, and I don't even include it in my model. And instead of the A matrix, I can just use the X matrix. Okay, so in this case, this is what we would write before, but what does this approximately equal to mean? Here we're being a little bit more precise. Now we're going to say, okay, the difference between them is this vector of epsilons, and I'm going to say the epsilons, these are my noise terms, are independent, identically distributed, Gaussian, with mean 0 and variance sigma squared. So now I have a probabilistic model that relates y and beta. Before, I just had a very rough, intuitive model that didn't really tell me too much. Okay, now that I have this probabilistic model, I can write the probability of y given beta, or this is just sort of a notational thing. You could also write it this way, probability of y given beta and x. It's up to you. They mean the same thing. But this is the form you get. This is just, this is because we have a multivariate Gaussian. Okay, so there's a couple steps involved. It's not too bad, but you have the exponential of a scaled Euclidean norm, which is the difference between y and x times beta. So now that we know this, the last step is maximize this expression over beta. When you first look at it, it looks kind of complicated, right? Because of all this other stuff going on. So instead of maximizing this, let's maximize the negative log. When I take the log, it kills the exponent. When I take the negative of that, it kills the minus sign. And then, also, the other thing is when I take the log of this, I get the log of the numerator minus the log of the denominator. But the minus log of denominator does not depend on beta, so I can actually ignore it for the optimization. So all I have left after all this is minimizing this scaled 2 norm. And we know exactly this is the same problem that we sort of just decided to do this last time without any justification in Unit 2. Now we're very well justified. We're saying if this is Gaussian, then this is the likelihood, then this is exactly what you want to do. And we know that the solution to this is just the least squares estimator. Okay, so to summarize, under Gaussian noise and this linear model with x and beta, the maximum likelihood estimate is just the least squares fit. So one place where this is a little bit useful is if I told you, instead of this being Gaussian, what if it had a different distribution? Like what if it was Laplacian or something else? It turns out that when you go through this whole procedure, you will probably find that this is not what you want to do. There's something else you want to do instead that's going to work better. And in fact, this is, so if these errors are what they call heavy-tailed, which means once in a while you get a very big value, then this is a very bad idea. Least squares estimates will get very confused by those outliers, and you instead want to do something like minimize the L1 norm instead of L2 norm, and that's going to work a lot more robustly. And this all makes sense once you understand this maximum likelihood framework. You can make an assumption about your noise based on maybe something you know, and then based on that, you can design the right kind of estimator. Okay. But for now, what's kind of cool is that we were actually able to recover our least squares estimator in a more principled way based on this model with Gaussian noise. Okay. Is this making sense? So there's one application. You'll get several chances to practice this sort of stuff on the homework. Okay, so this brings us to the next idea, which is what if I know something about beta in advance? So previously, we didn't know anything about beta. What if I know something about beta? So here's a slightly different idea. What if I maximize the probability of beta given y? And let me make in ML, what we did is we did arg max over beta probability of y given beta. Do you see how these are different? Previously, we said maximize the probability of y given beta. Now we're saying maximize the probability of beta given y. So these are actually different things. This is asking the question, what's the most probable beta given the measurements y? Now it turns out that in order to even make sense of this, you have to know something about the prior statistics on beta. By prior, we mean the statistics on beta before you ever see any data. So that's why it's prior. Okay, so how do we do this? There's this thing called Bayes' rule. We talked about this briefly last week. Bayes' rule is what you can use if you want to change the order of conditioning. So here's an example where we want to write this p beta given y in terms of this more familiar quantity py given beta. So to do that, we have to just multiply by p beta here and divide by py. So now I can see, okay, if I want to maximize probability of beta given y, that's the same thing as maximizing this whole ratio over beta. The y on the py on the bottom doesn't matter for this maximization, so it's just a constant, so I can kind of forget about it. I really just want to maximize that numerator. And now you can see I'm actually maximizing the product of the likelihood, which is what I was using in maximum likelihood estimation, and something else, which is something else I have to know in order to do this. So I have now two things. I have the likelihood, how well beta agrees with the data x and y, and the prior, how well beta agrees with my prior knowledge of it before I ever saw any measurements. So those are two different concepts. So this approach, MAP, uses both the likelihood and the prior, where maximum likelihood uses only the likelihood alone. Okay, so any questions on this? Let's see an example. So we said that MAP can be written this way: maximize over beta, the likelihood times the prior. We also know that I can put a minus log in there and change the max to a min. And if in this case, if I do that, if I take the log of a product, that's the same thing as the sum of the logs. So finally, you can see that another way to write MAP estimation is to minimize this cost. I have the negative log likelihood, and then I have the negative log prior. So let's look at this linear Gaussian model that we saw before. So again, the noise are identical, independently distributed Gaussians. We know that the likelihood is this. That's exactly what we saw a couple pages ago. But now we have this other term. This is the log of the prior. And if you just rewrite this in a slightly more convenient way, like, okay, I'm minimizing this whole quantity. So that means it's equivalent to minimize 2 sigma squared times this quantity over beta. So what I do is I just multiply through by 2 sigma squared, which moves this guy over to here. And now all of a sudden you can see this is exactly in the form of regularized linear regression. So here we have our RSS that we want to minimize, but now we also want to minimize, we have a penalty term. And you can see that the strength of the penalty is going to be proportional to the noise variance, sigma squared, of these guys. And we have to make a choice about the prior. That's going to determine the penalty function here. So let's look at a couple choices. What if our prior belief is that our beta coefficients are zero mean Gaussian with a particular variance v? So we would choose this variance in order to say how close they are to zero or how large they can be. Okay, so this is what the PDF looks like. Because they're IID, this is a product of individual Gaussians. Zero mean means there's no subtracting of mu here, and the variance shows up here and here. This is just the standard Gaussian. So if I take the log of this, I'm going to take the log of a product, which is going to give me the sum of the logs of these, and the log of the exponent cancels that. This ends up just being a constant, and what remains is this here. So now we know for this prior belief what the log p is. I can plug that into here, and I find that my penalty, my phi, is exactly this. So here we see this is exactly ridge regression for alpha equals sigma squared over v. So you're somehow balancing the noise in the measurements and your prior belief on the variance of betas to choose that alpha. So this is an explanation of what ridge regression is. It's map estimation under a Gaussian prior. What about Lasso? If we believe in advance that beta is Laplacian, and so Laplacian looks like this. So it has a peak. It goes like this. This is the PDF. When you look at the log of this PDF, you get the L1 norm. And so finally, you get this regularization term. And that's Lasso with alpha is 2 sigma squared over this lambda. And lambda is the width parameter in your Laplacian. So we can now see exactly where Lasso can be interpreted as a map estimation of beta for the quadratic, or the Gaussian noise model and the Laplacian prior. So it's a way of understanding all these techniques, which until now have been sort of, ad hoc. Now we actually have a framework to understand how they all fit in. And if someone tells you that there's some other distribution about beta that you should believe in, then that will give you some other penalty, and you'll be able to justify why you're using that penalty. So that's pretty much, that's almost all we have to say. So this is just an estimate, a summary. We can think about machine learning as statistical parameter estimation. We start with a probabilistic model that relates our parameters that are unknown, that we have to learn, to our data y. And then we estimate those parameters by maximizing the likelihood or minimizing the negative log likelihood. We have to do this in general using some optimization algorithm. We'll talk about those in Unit 6. That's one approach. Or if we have some prior belief on thetas, then we can add that to our likelihood, and we can do map estimation. So there's different ways to notate this. In this notation here, the training features, I'm not writing those explicitly here, but they are implicitly included in this. They're buried in the likelihood. So I go back and forth about whether I want to write it with the x there or not, but just remember that they're there, even if they're not explicitly notated. Okay, so I think that's all we have time for today. Any last questions? Okay, great.